Okay. All right. So today is all about the midterm. So again, the midterm has been rescheduled to Monday. So it's going to be, whoops, I think that's the 6th. So Monday, and you can take it any time between midnight to 11:59 p.m. Okay. So there won't be any live lecture. There won't be any live lecture next Monday because maybe this time works best for you, and so feel free to take it anytime. It'll be 2 hours, and what's important is you have to use the lockdown browser. If you try to use a different browser, it will require a password that I don't even know. Okay, and so it just won't work. It won't give you access to the exam, and so you have to do it, download the lockdown browser, open it up, and then it should take you, to your CMitch Blackboard account, and the exam will be in the assignments link. And so you click on assignments, and you should see, I think it's in capital letters, lockdown browser midterm 3. And when you click on that, it'll go through this whole test of your webcam, microphone, all that stuff. You have to take a picture of you, a picture of your ID, and all that stuff. And then afterwards, it'll open the exam for you. And then you can't stop it, like your homework assignments. You can do a few questions, come back to it. This you have to sit through. So, go to the restroom, everything before the exam. And then, yeah, you'll have a full 2 hours. You won't need it, I'm sure. But you've got it in case you need it. Okay, 30 questions. And so today I'm just going to go through this practice midterm that has, I think there's 40 questions on this. Okay, and the types of questions, it's going to be chemistry content, like balancing equations, moles, grams, all that stuff. Shapes of molecules, like this first question. And then there's going to be some from the reading. So make sure you read chapters 3 and 4 because there will be some questions about, what is the carbon cycle or climate change or, the greenhouse effect, all of these things. Okay. All right. So any questions, just kind of general before we get into the midterm?
I do have a question. I tried to
Yeah.
do the lockdown browser today, and it
Okay.
said that we needed a link from Blackboard in order to download it because there was only like a 2-month free trial thing, but it was a
Oh,
bit
yeah.
confusing.
Yes, I will send you. It's if you Google lockdown browser C Mitch, it'll pull it up for you. But I will, after we get off the call today, I will send out an email through Blackboard that will take you right to that page.
Thank you.
Yeah, you're welcome. Yeah, and it'll give. I think it says instruction or here or something like that on the web page. You click on it and it'll give you all the instructions on how to do it all. So, okay. Okay. Any other technical problems with lockdown that you're experiencing? I guess today or this week is the week to get it sorted out. So I'm glad you're doing it ahead of time. Okay. Nothing? All right. So hopefully you've had time to at least look at the questions on this exam. This homework assignment. There is no deadline for it, so you can take it right up to Monday if you want, or even beyond. So if you want to review this, even for the final exam, you can come back to it. I have unlimited attempts for this one, so you can keep trying it and trying it. Of course, we're going through the answers here today, so I encourage you to still try the questions on your own, and then maybe refer to this video later if you have questions or something. But yeah, do try the questions yourselves. Okay, so this first one, it's asking really about the shape. And so these kind of relate to, what is the shape of the NO2 minus molecule? And so for this one, whenever it's asking for shape, that means that you have to first do its Lewis structure. and then apply that VSEPR theory to figure out what its shape. Okay, so that's kind of step one and then step two. Okay, and so this one, I guess it's not really shape related because it's not asking like angles and stuff. So I guess probably for this one, it's just really Lewis structure, I guess, because it's asking about like single, double bonds, that kind of thing. And so the Lewis structure, what do we need to know to draw a Lewis structure?
The valence electrons?
Yeah, so all of the valence electrons. Okay, and if it is an ion, a negative charge means that you add one more to that total. Okay, if it's 2 minus, then you add 2 more. If it's plus, then you take 1 away, etc. Okay, so this one would have how many valence electrons then? So just as a little review, so valence electrons, remember we kind of skipped this transition metal series and we count from here. That's 1, 2, 3, 4, 5, 6, 7, 8 valence electrons in any of those groups. And so that means nitrogen will have, if you just count 1, 2, 3, 4, 5 valence electrons, and oxygen will have 6. Okay, so we will have 6 times 2 for the oxygens, and then another 5 for nitrogen. Okay, so that's, what is that, 12 and 5, so that's 17, and then you add 1 more, so 18 total. Okay, so does everybody get that it's 18 electrons? Okay, and then we put the atom in the middle. Okay, so in this case it's nitrogen. It's, unless it's a more complicated molecule, the atom on the left of the compound, in this formula, that'll be the one that's in the middle, and then these ones will surround it. Okay, so you have N, and then you have oxygen on either side. Okay, and then you start with single bonds, so you're trying to get to 18, so we'll do 1, 2, 3, 4. Okay, and then you start to build up electrons around all the outsides. So we place 4, so we go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So then what do I do with the other 2 left over? They go on the middle. Okay, if you have any left over from that 8. So now I've got 18 electrons. Okay. And so now, what is wrong with this structure as I've drawn it? So, in other words, this answer, why is that not right? 2 single bonds.
Because both of them require a perfect contact.
Exactly. So remember the atoms that absolutely have to have an octet. And, the only real exceptions to that are if you have an odd number. So things like NO or I guess NO2, okay, things like that, they'll have an odd number. And then, you'll have to, whoops, you can't see that. Let me move this. There we go. Go down. Okay, so NO or NO2 are exceptions, so they will, have to have the middle atom not having 8 electrons, but the atoms that absolutely have to have an octet are carbon, nitrogen, oxygen, fluorine, and neon, but there are really no compounds with neon just because it's a noble gas. And then, so these 4 in practice absolutely have to have an octet, or 8 electrons around them. These, down farther, they can have 8, and they very typically will have 8, but they could have more than 8 electrons. And then this group will typically have less than 8, as well as this group. Especially, really the only ones you're going to see are beryllium compounds. beryllium will also have less than 8. Okay, so beryllium is a exception, as well as the group 13s, as far as having less than 8. Okay, so this one, nitrogen, oxygen, they have to have a octet. So the way you do it is you say, yeah, I'll do that, and put one there. Okay, and so that's one of the possibilities, and this is a resonance form because I also could have chosen the double bond to be over there, right? So like that, okay? So if you look at this, it really will have two identical bonds intermediate between a single and a double, because it's kind of just a hybrid between, this one and that one, okay, where each bond is really, either a single or a double, okay? So any questions about that? Okay. This answer would be correct if there were no resonance. Okay, but since there's resonance, that's not right. And, that's not right. Okay? All right. 1 mole of oxygen contains the same number of molecules as, and beware of questions where instead of this, I might just say this. Okay, in this question, it really doesn't, matter. But remember the elements that have to be diatomic, right? So it's hydrogen. So looking at the periodic table, it's H2, N2, O2, F2, Cl2, Br2, I2. So there's 7 of them. And remember that it forms that little 7 here. Okay, plus hydrogen. Okay. And so anyway, I just didn't want to forget mentioning that today. In this case, 1 mole of oxygen will contain, and then you've got different possibilities here. Really, this is just exploiting that 1 mole of anything will equal 1 mole of anything else. Okay, so this, it doesn't matter what the identity of it is. Okay, it could be that, or it could be oxygen or ozone or any other molecule. As long as there's 1 mole, that will be the same as 1 mole of oxygen. Okay. Now, if you're talking about, how many atoms or things like that, then that will differ, right? Because this one has only 2 atoms per molecule. This one has a whole bunch more. Okay, so that will differ. But if you're talking like moles of molecules, then it's going to be the same number. Okay. All right. And yeah, as I go through these, text your questions, stop me, with Mike, with your audio anytime if you have questions. Okay, this one, I have one, I believe, like this on the exam in words where it's, you have to write out the equation. Aluminum metal, how do I write that? So it's just the element. I don't do Al2 for this, right? I don't do that. Okay, so it's just aluminum reacts with, and I'll let you think of this one. So iron 2 sulfide, what is that formula? Okay, so remember that 2 implies that it's a 2 plus charge. And then what is sulfide? So sulfide is 2 minus, right? So it's just going to be that. Okay. Yeah, so it's aluminum plus FeS, and then you're going to form aluminum sulfide. So again, so aluminum has that, sulfide is that. So what is the formula for aluminum sulfide? Al2S3, yep, exactly. Okay, plus iron metal. Okay, so that is your unbalanced equation. So now it's just asking, what's the coefficient for aluminum when it's balanced? Okay, so if you look at 2 on the right side, so you need a 2 there. And then, it's not asking the irons, but you then could look at the sulfur. So you're going to need a 3 there and a 3 there. Okay, so that would be the full balanced equation, but it's just asking aluminum, so that's 2. Okay. Sometimes it might be a question where what is the number if you add up all the coefficients? And you would include all the 1s in here too. There's a 1 in front of this one, okay? And so in that case, this would add up to 2, so it's 5, 6, 7, 8, 9. So the total would be 9. Okay, so just, look at how the question, read the question really carefully. Okay, it may either ask, like this one, what is it for just one particular one in there? Or it might ask, add them up and what's the total? And don't forget the 1s in that case, okay? This is just from the reading, so I threw in a mixture of these just to again reinforce to read the chapters. So as ozone hole gets more pronounced, one expects incidence of skin cancer too, and this is pretty obvious. Okay, so it's going to increase worldwide. Okay. Balance the chemical equation, and here's your first mole gram question. So what would the coefficients be for balancing first? Yeah, 2, 3, 1. Good, good. Yeah, so 2, 3, and 1. Okay. And now you have 10 grams of aluminum. Okay, and you want to know number of moles in this case, not grams, but of iodine. Okay, and so what is I guess our first step was to balance. What do we do now? What is our next step in this question? So you're given grams of something, so that's your red flag. Yep. As soon as you are given grams of something, you can get its moles by using the molar mass. And you divide by here I guess it's just the atomic mass because it's just aluminum. Okay, so aluminum, let me see. I have to look this one up for its exact one. Aluminum is 26.982. That's grams per mole. Okay, so 10 divided by that. 10, and then 26.982. So that's 0.371 moles of aluminum. Okay. So now, how do you get the moles of iodine? Yeah, so you look at the
ratio, and then you could find it in grams and then convert that to moles.
Actually, it's even more direct than that. So you're right. Yeah, you just look at these ratios, okay, and it's a 3 to 2 as far as iodine. Okay, so iodine to aluminum is a 3-to-2 ratio. Okay, and so that means that you will then multiply by 3/2. Okay, or in other words, you're going to divide by 2 and then multiply by 3. Okay, and so once you do that, you will have directly the moles. Okay, so that's just the way to convert moles of something into moles of something else. And so if you do that times 3 divided by 2 is 0.556 moles. Okay, and then I think you were thinking, if you wanted grams, then you have to, use molar mass or something. So then if this were asking, how many grams of aluminum, then you'd have to take this and multiply by the, molecular weight or molar mass of iodine. Okay, and then that'll give you grams. Okay, so any questions about that one? Okay, so you calculate moles of aluminum and then just do the conversion using those ratios. Okay. This one is a little different question. I wanted to throw this out there to see if you had any ideas. So mass percent of chlorine in that compound. I guess any ideas of how you would do this question? How do we figure out mass percent of chlorine in that? Yeah, chlorine by the molar mass. Yeah, so this is really saying, so it's mass percent. So we want to just know really the molar mass, or the grams per mole of all the chlorine content divided by the grams per mole of the total compound. Okay, and so there are 3 chlorines in that compound. Okay, and so all you're going to do is just take the molar mass of one chlorine, it's from the periodic table, times 3, okay, divided by the total of that whole compound. So that is, what is it, fluorine is 19, oops, fluorine is 19, chlorine 35.45, and carbon is 12. So 19, and then we've got 35.45 times 3, and then another 12 for carbon. So that's divided by 137.35. And then it's a percent, so you have to, multiply by 100% there. Okay, and then the 35.45 times 3. Okay, so we have 106.35 divided by 137.35 times 100%. Okay, so this is the molar mass of the 3 chlorines in the compound. This is the molar mass of the whole compound. Okay, and so if you divide those out, you get 77.4%, but it's, the closest one. Okay. All right. The best Lewis structure for boron trifluoride. So here it's the usual strategy of, all the valence electrons. And so fluorine has 7 each, and boron has 3 valence electrons. So that's, 21 for the fluorines, 22, 23, 24 total valence electrons. Okay, so then you put your boron in the middle, fluorine's out here, and so we've placed now 6 electrons, 7, 8, 9, 10, 11, 12, 14, 16, 18, 19, 20, 21, 22, 23, 24. Okay, and this is stable. It's an exception. It will have less than an octet. Okay, because it's in group 13. Or beryllium, again, is the other example, or the other exception. Okay, so it is totally happy with only 6 electrons. So in other words, do not do one of these numbers, okay, where you try to have a double bond in there. That does not happen with the group 13s. Okay, and then this just has too many electrons altogether. I think that one as well has too many electrons, and then this is trying to force it again with double bonds. Okay, so this is stable because it's a group 13. Okay. Lewis structure for this one. So how many total valence electrons for that one? And so ICl5. Okay, so everything is in the group 17 here. So valence electrons, you've got 6 atoms, right? 6 atoms total, each with 7 electrons, right? So 42 valence, yep, 42 valence electrons. And so again, put the atom on the left in the middle, and then everything else goes around it. So again, it's not asking for shape here, so it doesn't really matter how you put these around it. You can put a little star shape, we'll say. Okay, so it's, whoops, what am I doing? So chlorines go around it. And so now we've placed 10 electrons around the iodine, 10, 11, 12, 13, 14, 15, 16, 22, 28, 30, 34, 39, 40, 41, 42. Okay, they go around that middle then. Okay, so this is an example of something that can have more than 8 or more than an octet, right? Because iodine is down below this second period. Okay, so again, anything here, there, or anything below the second row can have more than 8 electrons. And in this case, iodine, whoops, I think I just lost connection. Iodine is surrounded by a lot of electrons, right? So you've got 2, 4, 6, 8, 10, 11, 12. It actually has 12 electrons around it, okay? But that's totally fine, okay? And so in this case, the best Lewis structure is, again, you don't have to force double bonds in it, okay? So the only time you use double bonds is if your central atom has to have an octet and needs it, and then you start to use double bonds. So, don't do any of these things, okay? So it just stays with single bonds, and make sure you have all the electrons you need, okay? So just that structure. Okay. Best Lewis structure for that one. Okay, and then I'm going to ask you the shape for it just to practice as well. So this Lewis structure, you'd have 7 times 2 for the chlorines, and then another 6 for the oxygen. So that's 20 valence electrons. So oxygen in the middle. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so now you look and say, okay, does everything that needs an octet, in this case the only one that really needs it is oxygen, does it have 8? And it does. Okay, so that is the best Lewis structure. Okay, and so the question I have for you is this the best shape for it? So this is saying that it's linear. Is that correct? Yeah, Lexi is right, okay, because this cannot be linear because the central atom has at least one lone pair. So as soon as you have at least one, like even that one, if that were the best Lewis structure, this also would be bent. okay, because you've got one lone pair. This one would also be bent, okay, because now you've got two lone pairs. And remember the trend that, it's linear if you don't have any lone pairs. If you have one lone pair, then maybe the angle goes to that. If you have two lone pairs, maybe it goes to that. Okay, so whoops, you can't see. Darn it. There we go. Okay, so that would be linear. That's one lone pair in the central atom. That's two lone pairs. Okay, so the more lone pairs you have in the central atom, the more this angle shuts down. Okay, so you're getting more repulsion between these electrons and the lone pair. Okay. All right, whoops. All right, so the next question. Covalent bonding is, okay, and so just definition, so it's sharing of electrons. Okay. Transfer of electrons, that would really be ionic bonding. Okay. Again, just another definition from the reading here. So ozone is destroyed in the spring in Antarctic, and it has to do with these ice crystals, so those polar stratospheric clouds. And it's a catalytic cycle, okay, where you've got these clouds, and then you've got those different gases that attach to it, okay, along with your CFCs, okay, and so then, a bunch of complicated reactions happen where you get chlorine radicals, and then that goes after ozone. Okay, so then you go like O2 plus O. Okay, so I'm not going to ask specific questions about those detailed reactions, but just you should know some of these real basics that, you need polar stratospheric clouds for this to happen is a big one. Antarctic is where it happens more than the North Pole, for instance, the Arctic, just because these are formed more readily here. Okay, so those big, I guess, points should be known. Okay. This one, number of valence electrons. So this, is no structure to draw, just, how many valence electrons. So you've got, for the iodine, 14 and then another 8. Okay, so what is that? 22. Okay, so 22 valence electrons. All right. This one, if we've done Lewis structures for compounds. If you have an element, then you just literally put, how many valence electrons it has. So argon is, if you read across the periodic table, it's 8, right? It's in this group. So just put 8 dots around it. Okay, so that's the Lewis structure for argon. Okay, if it were asking what's the Lewis structure for nitrogen, an atom of nitrogen, then you'd have 5 electrons. So you could really draw it whatever way you want. You could say 1, 2, 3, 4, 5, or you could do 1, 2, 3, 4, 5, or something like that, or any of those possibilities. Okay, as long as you have 5 dots around it. Okay. How many lone pairs? So pairs mean 2 electrons. Are on the phosphorus atom in PF3. Okay, so you've got 21 electrons from the fluorines, then another 5 electrons from the phosphorus, so 26 valence electrons. So that, what is that? 1, 2, whoops, 2, 3, 4, 5, 6. 24, 25, 26. Okay. And so this only has 1 lone pair of electrons. Okay, so again, read the question carefully. If it said, how many electrons are on the phosphorus, then there'd be 2, but it's really just 1 lone pair. Okay, and here's a question for you. What is this shape? So this is one of those 5 shapes that you should know. So you've got 3 things bonded to the central atom, so it's trigonal something. Trigonal pyramidal, correct. Yeah, so if you have a lone pair on the central atom, it's trigonal pyramidal. If you don't, like this one, where was it? Right here. This is trigonal planar. Okay, so no lone pair. Okay, so that's the difference in those. In both of those, you've got 3 things bonded to the central atom. It just boils down to whether you have a lone pair or not. Okay. Then how many moles are in 1.5 grams of ethanol? And then it has this formula. So the strategy is you have the grams, and then you're going to divide by the molar mass of this. Okay, so if you'll have access to any periodic table you want to use. So that, let's see, we've got 12 times 2 carbons. And then 3, 4, 5, 6 hydrogens. And then another 16. So that's 46.06 grams per mole for the whole thing. Okay, and then 1.5 divided by that is 0.0326 moles. Okay. How many moles of boron trichloride are needed to produce 25 grams of HCl? So this is maybe one of the toughest questions on the exam. So for this, where do you start? Yeah, so make sure it's balanced. Yeah, so let's see. So 1 boron, 3 oxygens, 6 hydrogens. Yeah, so this is balanced. Okay, so that's nice at least. And then 25 grams of HCl. So then we have to do its moles, right? So that will be 36.45 grams per mole for HCl. Okay. And remember, this I can't stress enough. When you are looking for this, the molar mass, do not use that number, the 3. Okay, it's just for this compound. Okay, the only use for those numbers in front is to convert. In this case, we want to do conversion of this to this. Okay, so it's going to be a 3-to-1 ratio. Okay, that's the only purpose for those numbers. Okay, so so this is just from 1H and 1Cl. Okay, from the periodic table. So 25 divided by 36.45 is 0.686 moles of HCl. Okay, and now it's a 3-to-1 ratio, so I have to divide by 3. Okay, so divide by 3, and that's your 0.229 moles. Okay, and again, if it asked for grams, then you'd have to multiply by whatever BCl, the molar mass of BCl would be. Then that would give you grams. Okay. How many moles of copper 2 oxide can be produced from that? Okay, so in this case, you're given, instead of grams, you're given moles, so that cuts out an extra step for you. Okay, so you're given that. And you want to know how many moles of this. Okay, so the names for this again, that would be copper 1 oxide. This is copper 2 oxide. Whoops. Okay, so how do you calculate this? So you see the answer there. How did you get that? So we're going here to here, okay? And the ratio is between copper oxide to Cu2O is 4 to 2, or in other words, 2 to 1 ratio. Yep, so you are just multiplying by 2. Okay, so 0.45 times 2 is 0.9. Okay, hydrogen gas. Okay, and on the exam, I may not be nice enough to give you that. Okay, so remember that. Okay, so hydrogen gas is H2. But let's see. How many molecules are present in 1 kilogram? So what do you do here? So how many molecules? We haven't done one like that yet. And I guess the feedback, whoops, it's kind of... Oh, the previous problem? Okay, yeah. Yeah, so you were told moles of this, and so it's a 2 to 4 ratio. In other words, it's twice the number of moles of that product. So that's why we have to multiply by 2. Okay. All right, this one, if we want to know the number of something, so how many tells you Avogadro's number. Okay, so I'm going to have that on the exam for you. You can look it up as well, but I'll have that on the exam. I'll make sure today that on questions that you need it, at least one question on the exam, I'll have it so that you could refer back to it. And so that's Avogadro's number. And so remember the little flow chart where it's moles, grams, and then number. Okay, and so we are starting here. So we have to first calculate moles, and then from moles we have to go to number. Okay, so in between here, we are going to divide by the molar mass, and then we're going to multiply by Avogadro's number. Okay, remember to get away from moles is multiplying by something, to get back is dividing. Okay, and so here you have 1 kilogram, and so it's most convenient to start always from grams of something. Okay, so that would be 1,000 grams, okay, of hydrogen. And so hydrogen gas, if you remember that it's diatomic, so you have to divide by that molar mass, so it's divided by 2. Okay, so that will give you, right around 500. Let's see, 1,000, 2.02, so that's 495 moles of H2. Okay, and then we multiply by Avogadro's number. 6.02 e to the 23rd is 3 times 10 to the 26. Okay, so really 2.98. Okay. So here's another question. What if this asked, instead of how many molecules, how many hydrogen atoms are present? What would you need to do? So this is hydrogen molecules, the total of those. No, it's not even that deep, actually. So you don't have to do the Lewis structure, but it's just really saying that each hydrogen molecule contains 2 hydrogen atoms, right? So you would just take this number and multiply by 2. So therefore, 2.98 times 10 to the 26 times 2 would give you hydrogen atoms. So let me just do that here. So times 2, so that's 5.96. Oops, I lost connection. There we go. So that's 5.96 times 10 to the 26 hydrogen atoms. Okay? So do you get that? Okay, so there are 2 hydrogen, so 2 H atoms per hydrogen molecule. Okay? So again, yeah, read the question carefully to see, what it's asking. Okay. The strongest bond. Okay, so covalent bonds, remember, are just, you're sharing electrons, right? So in this one, you have 2 electrons. That one, you would have 4 electrons between them. That one, you would have 6 electrons. So each line is 2 electrons, okay? And so the more electrons you have between the atoms, the stronger it's going to be, right? Because these serve as really a glue to hold the electron or the atoms together, right? So triple bonds will be strongest than double, which will be stronger than a single bond, okay? This is just a definition, so remember, light can behave as a particle and a wave. Okay, so it has wave-particle duality. Highest electronegativity between these. So if we look at the periodic table, okay, so which ones again? So it's arsenic, scandium, phosphorus. So arsenic, and then scandium's way over here, phosphorus is up here, and then what was another one? Sulfur, okay, was the last one. Okay, so between, I guess if we do it kind of incrementally, between scandium and arsenic, okay, remember, electronegativity increases as you go this way and as you go up. Okay, so left to right and bottom to top. And so that's going to be the least electronegative. So arsenic is going to be so far the highest. And then between phosphorus and arsenic, that's going to be more electronegative. And now between sulfur, now it's farther to the right, so closer to fluorine, remember? So that's going to be the highest electronegativity. Okay, so sulfur. Okay, so again, so electronegativity, it increases as you go that in a group or left to right in a period. Okay, so just remember fluorine is the most electronegative. Okay. Montreal Protocol, so, from the reading, again, so it was a treaty to reduce the amount of CFCs produced. Okay. That ozone, so the structure for ozone is we've got 18 valence electrons, so as you may remember, it looks something like this. And then you've got this one. Oop, if I move that. over here for now. Like that. Okay, so that's a resonance form. And so this is saying that the O, so the angle here, is not exactly 120 because, and again, it has to do with this lone pair. Okay, so this is repelling these electrons, and so this angle, or the lone pair, takes up a lot of space, and it starts to repel those bonding electrons. Okay, and so as a result, the angle on this is actually more like that. Okay, and so its angle is, all you can say really is it's less than 120 degrees. Okay, so if it were this, where you have three things bonded to it, then remember all these angles are trigonal planar geometry. All the angles would be 120 degrees. Okay, but if you replace one of these with a lone pair, now you start to get repulsion here, and this angle becomes less. Okay, so it's, I don't know, maybe 110 or something like that. Okay. Go like this. There. Okay. All right, the next one, international agreement to reduce greenhouse gas emissions. So this was the only one that the world could really agree on, Kyoto Protocol. It's really something we talked about at the last lecture on Monday, so I'm not going to really get into that on this exam. So, I put this on there just to remind you, to read the chapters, but the context questions will generally come earlier in the chapter for chapter 4. So things like the carbon cycle, greenhouse effect, all of that. For sure, read that. And then in chapter 3, make sure you know about CFCs and then what possible replacements that came out, like the HCFCs and other ones that we talk about in that section, okay, where they try to replace it with like hydrogens and stuff. Okay. This one is the balanced chemical equation. So A is unshaded and B is shaded. And so I would just write out, all the molecules you see here. And so if B are shaded, then you'd have, or I guess let's do A is unshaded. So we've got 4A is reacting with 1, 2, 3, 4, 5, 6 B2s, okay? And then you're going to have 4 AB3 molecules, okay? And so does that make sense based on, what is present in the boxes? Okay, and then when you balance an equation, you should always do a final check to see, can I divide everything through by some integer, non-1 integer. And so here, I can divide everything through by 2, can't I? And so I could say that that is 2, 3, and 2, okay? And so the best balanced equation for this whole thing is this. Okay, so the questions like this, they usually won't have both of these as possibilities. Okay, but in case they do, always pick the one that has the lowest possible coefficients, okay, that you can't. Now, I can't divide everything through in this form, okay. Geometry for this one, ammonium. This is the ammonium. ion. And this one, so you've got a total of 9, so 8 valence electrons. Okay, so you've got that. So it's just this. Okay, and remember, hydrogen is totally fine with, whoops, lost connection again. I don't know why it's doing that today. There we go. Okay. But hydrogen is totally fine with 2 electrons around it. Okay, so that so that's the Lewis structure. Okay, so 8 electrons like that, and so this is in that list of geometries you should know, and it's tetrahedral. Okay, so this would be your what I called AX4 in the PowerPoints in your notes. Okay, so 4 things around it, no lone pair around this center. Okay. The identity of substance X, if you have this. So any ideas? What would you do here? Here. So you've got its mass, you've got its moles. So no ideas? Yeah, so remember molar mass, the units for molar mass is grams per mole, right? And so you could just do that divided by that, okay, 17.5 for this one is 17.5 grams divided by 0.380 moles. Okay, so that is 17.5, 0.38. So that's 46.1 grams per mole. Okay, and then just look at the possibilities here. So just look at these different options and see which ones of these add up to 46. Okay, and you have that one. So this is 16 times 2 plus another 14. Okay, equals 46. Okay, any questions about something like that? Okay, the mass of 0.5 moles of that. Okay, so here were moles. So in that little flow chart that I showed earlier, where is it? Right here. If I move the chat box here. There we go. Okay, so you have this time. Now you want to go to grams, so we're going to multiply by the molar mass. Okay. Oops. All right, so let's go back to that one. There we go. So 0.5 moles. So 0.5 moles. And if you multiply by that grams per mole, so if we kind of estimate, so 35.45 times 2, that's the chlorines, and then we've got 19 times 2 for the fluorines, and then 12 for carbon. That's 120.91 grams per mole times 0.5 is 60.5 grams. Okay. The mass of a single chlorine molecule. Okay, so in this case, a single, so that just means one, right? So we've got one molecule divided by Avogadro's number. Okay. So that will give you the moles. Okay, so 6.02 e to the 23rd. So that's 1.66 times 10 to the minus 24 moles. Okay. And then now we want to know mass, and so we're going to multiply by 35.45 times 2, so times 70.9. And that's your 1.178 times 10 to the minus 22 grams. Okay, way too many sig figs here, but yeah, that's the answer. Okay, so here is where you have to look at the answers to see which ones make sense. And here you could instantly get rid of 2 of them, right? If you have a single chlorine molecule, it's going to be an insanely small mass, right? So these are gone instantly. So it really kind of boils down to 2 of them. Okay, so those are kind of in the realm of being possible. Okay. All right. What's the mass of exactly 500 sulfur atoms? Again, it's going to be really, really small, so forget about that one, forget about that one. Okay, and so 500 sulfur atoms, you go 500 divided by Avogadro's number, and that will give you the moles of sulfur. So 500 divided by e to the 23, so that's 8.31 times 10 to the minus 22 moles of sulfur. Okay, and then you multiply by the 32.1 grams per mole for just, we're talking sulfur atoms here. Okay, so times 32.1 gives you 2.66 times 10 to the minus 20 grams. Okay. The molar mass of this, so you're just looking in the periodic table, so cobalt, I don't know that one offhand, so that's 58.933. Nitrogen is 14 point, we'll do it exact here, 14 point, we'll say 01. And then oxygen, 994, okay? And so we're gonna have 1 cobalt, 2 nitrogens, and 6 oxygens, right? Because of the parentheses there. Okay, so that means 58.933. Then we got 14.01 times 2. And then 15.9994 times 6. And so that's 180, I get 182.9 grams per mole. But, I guess sig figs 183 is close enough. Okay. Molar mass of hydrogen gas. So this is a trick question, okay, because a lot of people want to do that. Okay, remember hydrogen gas is this. Okay, so you've got 1.01 grams per mole for each hydrogen times 2. Okay, is that. All right, geometry of AsCl3. Okay, so add up the valence electrons. So we have 7 times 3 for the chlorines. And then arsenic is, arsenic is in group 15, right? So it'll have the same number of valence electrons as nitrogen does. Okay, so that's 5. Okay, so that is 26 valence electrons. And so arsenic's in the middle, do that. that we'll say. So that's 6, 7, 8, 9, 10, 11, 12, 18, 23, 24, 25, 26. So this is your like AX3L variety, okay, which is similar to what we did for PF3 before, which you can't see. Okay, so remember PF3, okay, and so this will be our trigonal pyramidal because you have that lone pair on the central atom, okay. This is, yeah, a good one. Yeah, so what is the sum of the coefficients? This is what I was talking about earlier. Okay, so you balance the equation. And so when you balance it, let's do phosphorus first. Okay, then maybe hydrogen next. So that's 12, so let's do 6 there. And then hydrogen, or oxygen last. So that's a 16 on that side, so you need an 8 over here, okay? And so this is where when you add it up, don't forget the 1 in front of that compound, okay? So that is 9, 15, and 4 is 19, okay? So any questions about when they ask it like that? Okay. Which element can accommodate more than 8? Can exceed its octet? Okay, and again, carbon has to have 8. Oxygen has to have 8. Helium can't go more than 8. And so phosphorus is beyond that second row, right? It's right here. So it can have more than 8. Okay. Which one, the Lewis structure, which one is a Lewis structure for ozone? Okay, and this is a different way to indicate it. Okay, so this is the same thing as this. It's just showing explicitly all the dots. So if I draw those out, okay, does everybody see these? In that case, 4 dots mean 2 bonds there, okay? All right, and this isn't showing the resonance. Okay, we know that it's really this and this, right, without the lone pairs. Okay, but this is just one of the possible Lewis structures, okay? I guess looking at why these other ones are wrong, this one, for instance, this oxygen has more than 8 electrons, so that's a no. This doesn't have the right number of oxygens to begin with. And then this one also has too many electrons. Okay. Again, from the reading, so which is the most biologically damaging? It's UVC. Okay, so in the order, it's for energy, it's UVC, B, and UVA. Whoops, UVA. Okay, and so even though this has the lowest energy, it is quite harmful because it can go through to deeper regions of your skin. Okay, so look for questions related to that as well. Which represents Lewis structure for chlorine, so just the atom itself. So has 7 valence electrons, so just put 7 electrons around it. Okay. And S2 minus, okay, so sulfur has 6 valence electrons, but you're adding another 2 for the charge. Okay, so that's a total of 8 valence electrons, so you just put 8 around it. Okay, and then you indicate the charge as well. Okay. All right, and then I think the last question, so which region is of the UV spectrum is absorbed least by the atmosphere? And that is UVA. Okay, so this is fully, so that's 100%, almost 100% absorbed. okay, because that is what is corresponding to this. Okay, it's really, that is UVC. Okay, so that's why it's all absorbed in the upper atmosphere, as well as this, actually. Um, okay, so that also happens from UVC. Okay, this is UVB, can do this one as well. Okay, so because of these two reactions, UVC is 100% absorbed. This is, I don't know, like maybe like 50% absorbed or something because it is active for this reaction. Okay, and then UVA doesn't have enough energy really to cause these reactions, so it is, less than 10% absorbed. Okay, so that will get through and impinge to our skin. Okay, and so note, here's something to read, in the chapters as well. These where I draw it, like that one or that one. Remember with the dot, these are called radicals, sometimes called free radicals. Okay, they are highly reactive. Okay, because they're just looking for something else to pair up, give it another electron. Okay, so if you have two of these, for instance, they're going to partner up right away and form a bond here. Okay, and so yeah, just kind of for definition, another definition question I might ask, something related to radicals. Okay, and that's all it means, is that it's this kind of unpaired electron there. Okay, and that is it for the midterm review. So, I guess any questions? So chapters 3 and 4. Read the chapter and make sure you understand all the concepts as well. I guess I didn't have naming on this practice midterm, and that's not something I'm really going to focus on in the actual exam. I figured I would kind of skip that because you had a lot of other content to cover. So that's something on the final exam I will, ask more questions about, what's this name, for instance, where you have to I would give you, the sheet that's a carbonate ion, so that's, calcium carbonate. Okay, so for this exam, you don't have to study, all these complex names like that. Okay, but I could, like this one question I had earlier, right? I had iron 2 sulfide. Okay, so make sure you know those names, so in case I give a reaction in terms of words, which one was it? Yeah, like number 3. Okay, that you would be able to write the right equations for these. Okay, so do look over names, but I'm not going to focus a lot on it. But you may need to use it for equations, calculate moles or whatever, or balance it. Okay, so any other questions before we sign off then? Okay, all right. That is it for today, and yeah, let me know.